Alright, let's take a look at some calculus. Some of the calculus that we're going to be looking at is going to be routine, like this first exercise, and some of this is going to be problem solving using calculus and our understanding of calculus. So you'll see the difference as it comes along. If you've been through the study guide, you'll have seen some of these exercises and problems. In this case, I'm not going to be able to show this to you here, but I believe there's a video on haiku, and I'll share the link to that after this is done. Anyway, all of this is something that needs to be done on the calculator, especially right here. When you look at part C, it says how fast was the population growing. That means they're asking about the derivative. Remember, the function tells us where we are, derivative tells us how fast we're going. So in the first case, how many leopards after 2 years, you just put 2 in for t. But in the part C, how fast in year 3, you put in 3 for n prime of t. And that you need the calculator to figure out. So, again, there's a video on that. For now, let's look at some of the calculus we can write. For an exercise like this one, we have to pay attention to some of the details of a function and predict what the derivative and the second derivative would look like. So, what I observe is, in the intervals just highlighted here and here, the function is increasing, which means the tangent lines are going to have positive slopes. So I need to find derivatives whose derivatives who are positive when the function is increasing. You can see I've crossed out these two because these functions are negative when f of x is increasing. And in this case, it looks like positive when the function's increasing and positive when the function's increasing. I've also seemed to have spotted a second derivative because I can see a couple of things. Number one, when the function is decreasing, my first derivative is negative. Secondly, the steepest part of the decrease corresponds with the zero of the second derivative. In other words, the inflection point exists at the minimum of the derivative. Inflection, minimum of the derivative, zero of the second derivative. These are the characteristics. So the other thing we can observe here is, from this inflection point, the curve is always concave up. The second derivative is positive from that point up. From here, the concave down, second derivative is negative from that point down. So, I can identify then, graph 1 represents the first derivative, graph 4 represents the second derivative. So, moving on. In this problem, we have a function, and it's a quadratic function, f of x equals x squared minus 3bx plus c plus 2. Now what we have to do is we have to remember to treat 3b as if it's a regular coefficient like 7 or 25. C plus 2 is another single constant number. It's grouped together. Anyway, what we know is f of 1 equals 0. And we know f prime of 3 equals 0. So that's all we have to go on. I'm going to go off in faith, as it is a faith-based school, and see what happens when I find out what f of 1 is. According to the equation, when x equals 1, I replace x with 1, I end up with an equation that has only b's and c's in it. But the one thing that I do know is that f of 1 is equal to 0. So this is f of 1, 3 minus 3b plus c, and this is f of 1. It's equal to 0. This expression here must be equal to 0. Cleaning it up a little bit, I can see that 3b is going to equal 3 plus c. So we'll see what we can do with that. I don't really know where it's going to go, but I see now f prime of 3 equals 0, which implies I have to take the derivative. So I'm going to take the derivative of f of x. Notice that, actually, I think I had some faulty... No, I'm good. Yeah, sorry, I just got stuck on my own work here. Anyway, taking the derivative, we get 2x minus 3b, because remember, this used to be x to the 1, now it's x to the 0, so we get this. And I do know that f prime of 3 is equal to 0, so when I put in 3 for x, I get 0, and I can solve this equation and find that b is equal to 2. So once again, I didn't know where I was supposed to be going with this. All I did was I took the information f of 1 equals 0, put in 1 for x, and set that equal to 0. That gave me this equation here. I took the derivative of the function, found f prime of 3, set that equal to 0 because that's what f prime of 3 was equal to, and I put that here. Now that b is equal to 2, I can go back to my other equation, substitute 2 in for b, solve for c and get c equals 3. Just to make sure this is correct, I put in the 2 and the 3 where they belong, and I get a quadratic function, x squared minus 6x plus 5, and I verify that f of 1 does equal 0, and that f prime of 3 does in fact equal 0. I could even go in, find f prime of 3 equals 0, which means we have a horizontal tangent, the vertex of the parabola at 3, and I could also verify that 1, 0 is a point on the graph. So using technology, I know that I did my work right, and I understand deeply what's going on. Final problem in this video, and I'll make another couple more for some other select problems from the review packet that we've been working through. But in this case, we have a cubic polynomial function. The graph has been shown here, and it's asking me first, given this graph, it's cubic. It's got a maximum and a minimum, and an inflection point is labeled here, so I guess I'm going to have to find those things. Part A says find f prime of x, so I just have the function. I just need to take its derivative. Free stuff right there. Even if you're having trouble with a lot of the algebra I'm asking you to do, this should be a pretty straightforward process by now, I hope. Second, was asked to find the x-coordinate of m. M is a local maximum, which means that m is a stationary point. That means the derivative is equal to 0. So I take my derivative, I set it equal to 0, which is a factorable quadratic. You can use the quadratic formula or complete the square, but this is the quickest way in this case. And I find out that x could be -5 or x could be 1. Just looking at the graph, I can see here, when x is 1, we have a minimum, so x equals -5 has to be, what did it say? The x-coordinate of m. Found it. Done. Finally, for part C, it says there's a tangent line to the curve of f at 312. So I know that when in the function up here, when x is 3, y is going to be equal to 12. And I need to find the equation of that tangent line. So I just kind of drew this little tangent line here. So we're going to expect a line with a steep slope and a negative y-intercept. So how do I find the equation of the tangent line? I need a point, and I need the slope of that line. Since it's a tangent line, I'm going to use the derivative. If I find f prime of 3, that will give me the slope of the tangent line, which in this case is going to be 16, steep as I predicted. The point was already given to me at 312, so I'll use my point slope formula and find the equation of the line. So I've done everything that I need to do, but I want to make sure I'm doing all this right. So the maximum has to occur when x equals -5, and the line 16x minus 36 has to be tangent to the curve at 312. I put this information into Desmos and verify, and indeed a tangent line at 312 is a y-intercept of -36 and a slope of 16, because this is the information that I entered, and it's worked. So, moving on. We'll have in part 2 of the video, we'll start here with number 5. Thanks for watching.